So Daniel Ashlock is going to give the first talk on generating maps with the do what's possible representation.
And I think my co-author is in another session, or maybe he'll be here in a minute. He wasn't up this morning. So the do what's possible representation is something that comes from a problem in the American Mathematical Monthly in 1957. And I first encountered this when I was an undergraduate, and some professor that was checking to see if I was smart said, "Here, solve this problem," without explaining it to me. And I eventually solved it, and then it just lay in my memory for 20 years until I suddenly realized it was just what I needed to make synthetic DNA data for bioinformatics. And that worked fairly well. It allowed me to make a bunch of tunably random examples of DNA. Thank you, my co-author.
Hello.
And what happened is this funny technique that enables this representation just kept turning out to be useful. So first I'm going to explain what the heck the representation is, then I'll tell you how to use it to lay out rooms like the ones at the bottom, and then I'll explain why, right after submitting this paper, we thought of 8 other things we should have done. So, the do what's possible representation is a drop-in replacement for any representation that specifies a linear string of characters or commands. There are 2 parts. The first is the complex string generator, and it generates an infinite string in the sense that you can always ask it for another character, and it just keeps churning out strings. Then there's the generative possibility filter. So the idea is the infinite string generator is spraying out a series of commands, and only some of them make sense, so the generative possibility filter stands in its way and throws away the ones that don't make sense. And the best way to think of a complex string generator is as a really low-quality, evolvable random number generator. And by low quality, I mean it has a lot of pattern in it, and that pattern is actually useful. Okay, so that is the version I eventually came up with for the 1957 math problem. It's a self-driving automata. And notice that it's Mealy architecture, so like if you're in state A and you see a 0, you go to state B and you cough out 2 1s. And the fact it can cough out more than one character means that you can drive its input with its output to generate an infinite string. This thing goes like 0, I see a 0, 1, 1, I see a 1, 0, I see a 1, 1, I see a 0, 0, 0. And so it generates this string. And the problem in the Mathematical Monthly was, prove this is the decimal expansion of an irrational number. It turns out that sequence is in fact aperiodic, which means it's not going to fall into some sort of repeating pattern. Okay, now if you know what logical depth is, it turns out that these self-driving automata generate logical depth very, very efficiently. If you don't know what it is, don't worry about it. And what I'm doing here is I'm going to have these things, and they'll spray bits, but now I'm going to compile the bits into numbers. Originally, like I said, I used them as a source of synthetic DNA, and what you do is you can evolve them to have higher or lower levels of entropy, which gives you DNA that looks more and more like uniformly random DNA that was useful for testing a bunch of feature recognizers for classifying DNA sequences. And in fact, so one way you can measure the complexity of these sequences, and this is the, I want to say roughly Kolmogorov complexity, but you just take a window of width 8 and see how often things happen, and then compute the entropy of that empirical distribution. Now there's another self-driving automata that I believe makes something that's really easy to prove to be periodic, because it generates something like 011, 0111, 01111, 01111, and the ones just keep getting longer. But once I've got these bits spraying out, I can use them to place rooms. Now, when I place rooms, my fitness is going to be the square of the area of the rooms divided by the area of the bounding box of the room. So I'm encouraging it to lay down a lot of rooms and compactly. That's what the dividing by the bounding box does. And as the numbers come out, I just compile bits to make the following decisions by going like mod the number of rooms. Which room am I going to try to put a room next to? On what side? How big is the new room? What is the alignment of the room? You can slide it up and down once you know where it goes. And is the new room a corridor? And the generative possibility filter is really easy. Is there space for a room there? So this thing is going to go room, and the possibility filter will just say, don't put down the ones that overlap another room. And it works pretty well. the starting room, which is 4 by 4, is in red. And like in the left example, only one room got placed next to the starting room. In the right one, 3 of them did. And so red is starting, blue are corridors, which are just rooms of width 1, and everything I laid down is gray. You're guaranteed the room structure will be connected as a tree because you're putting rooms next to rooms, but in fact, the please be dense condition causes a whole lot of other reconvergence. And there's lots and lots of adjacent rooms. Also, we did this pretty quickly, which is why there are no doors or treasures or monsters or anything. One of the referees was quite upset that we just threw down a bunch of rooms. Okay, so the evolutionary, this is the slide that I was put in that I don't really need, and these details are in the paper. But the really relevant part is, with 2 exceptions, each fitness evaluation was initialized with a single 4 by 4 room. And we did a parameter study, and I'll have the results of that. The results of that were pleasant, though it turned out the parameter study was not very helpful. Now, if you look at the evolved map, it's obvious that if I choose a random room in either of those maps, I can't put a room next to it with probability about 0.9. It's just filled up around it. And so the recent room hack changes the rooms that may be selected as initial targets for adjacency placement to the 10 most recently created rooms. And that really speeds up how fast the thing lays down rooms. And probably since the room has the people in it that it does, you've all thought of 5 or 6 other better ways to do that. And so we did a parameter study where we checked the mutation rate, the population size, and then we did a study where we implemented the recent room hack and checked the number of states. And then we did 2 funny studies. One, I just ran evolution 10 times as long, and yeah, it fills in more rooms if you do that. And then we tried using a non-standard starting room. So that's a pretty sad parameter study. And the way you put a top spin on that is, the representation is robust to the choice of parameters. I mean, there's some advantage, but none of it is statistically significant. And so now it doesn't really matter which population size or mutation rate I choose. And then we did the state study, and it turns out that having too few states is bad, and the intermediate ones look slightly better, but again, the only one that's significantly worse is when the machine only had 4 states. But notice, 1,250, so that's around 1,200. Be up there. So the recent room hack meant every run with it outperformed every run without it. So it's a really good idea. And there's a no recent room hack, recent room hack. So, I think it got ahead by having much more area down, but it also had a bigger bounding box. But that's sort of unavoidable. So that shows that the recent room hack shows up in the phenotype in a very distinct way. And then, yeah, I ran things for longer and on a much larger board, and it had no problem filling the board. And then we also tried changing the starting room. Good, I'm doing fine for time. So instead of having a 4 by 4 room, we put a really long, like 2 by 32 corridor in there. And as you can see, changing the starting room really helped. And in fact, if you started with a C dungeon that had like room, corridor, you'd never get stuck because you'd have such a high surface area, in a sense. The notion of surface area, which is all the rooms where you could put more rooms, is sort of relevant to analyzing all this. And then this is Christoph's idea. He said something about, well, can they fill in something that isn't just an empty space? And it turns out the answer is yes. And he has this plan to do expressive range analysis in the future, which is where I learned about expressive range analysis. And again, I've used a giant room, but it had no trouble making a letter I. Maybe we should make a whole alphabet. And this is something we came up with after submitting the paper. This was in our vision paper answering the riddle of Toggleby, so it can fill in very irregular areas efficiently. Now, one thing we haven't tested that I think, let's not do the future work before getting to the future work. Okay, the recent room hack isn't a bad idea, but tracking failures to place next to a room and removing it from the active list after several failures is better. If a room can't place a room next to it, probably it really can't, and so you delete it from the active list. that tends to keep the placement of rooms near the surface of the growing structure. Clearly, the next pass of doors, opponents, treasures, traps, etc. is an early priority for future work. And we could put those in a way in the self-driving automata because it can keep making decisions about a room. Or it might be better to do it downstream by stealing ideas from EvoStar that has this huge track on architecture that actually tells you not only how to lay out rooms, but how to figure out which one's the master bedroom, ogre, or walk-in closet, treasury, yeah, whatever. So, now this is the thing I think I'm most excited about. I always evolve these things on a fixed background, but they're highly adaptive. They have a pattern trying to put down rooms, and it gets better at filling in the space you're testing it on. But I think if you challenged it with several different spaces and fitness evaluated on all of them, you might get something that's good at just generally laying out rooms into any sort of empty space or partially empty space. So in the past when I've done this, I always just coughed out the thing I needed. The idea of spraying bits and compiling them into numbers so that I can make a series of decisions that have different numbers of outcomes is original in this paper, but I've already thought of a bunch of other things to do with it. And then these rather large maps are specified by objects that contain 200 bits. So these are very, very compact ways of laying out huge numbers of rooms. And in fact, there's a control experiment I want to try where I generate 20 random bits and use it cyclically and see what kind of map I get out of that. And then there are, in other work I've done, I have a whole lot of other complex string generators besides the self-driving automata. One of them is a very simple GP system that only has 3 commands: print 0, print 1, and go to somewhere else, except the go to only works every other time you execute it, which means the go-tos can jump past one another and create a very complex system. Just to supply a little context, this same representation can evolve an 8-bit gray code in a couple of seconds. It actually can find a Hamilton path in an 8-dimensional hypercube quickly. So this seems to be a very powerful representation. I've done a number of other things with it. Sorry.
We have plenty of time for questions. Yes, Simon.
Yeah. So I think it's a nice representation. It's interesting. But have you done this kind of baseline that you could compare it with? That's just using a random number generator to give your sequence of strings.
Actually, my baseline was generate a random sequence of bits and use it cyclically. But no, I haven't done that baseline.
Because if you did that, right, you'd still lay out a bunch of rooms within your grid.
Yes, you could, and it would probably work moderately well. Something that isn't visible here because I didn't write it into the fitness function, though, is the random number generator will never give me a regular appearing way of laying out rooms, like a barracks or a dormitory. This can. But no, that's a good idea, and my just cycle through some random bits would be a similar baseline. Like I said, we did this in 3 weeks. You see, you people in SIG, I sort of agree with your hard deadline thing, but it causes me to rush my papers sometimes.
It's published well ahead of time, right? But it still comes as a surprise.
Maybe I think it might occur on the filtering side where you're looking at the adjacency of rooms in space. I think in the unconstrained spaces, in the earlier slides, you get quite a lot of diagonal patterns. Because I guess you're just saying, oh, okay, well, not that side, then that side.
Well, it's this side and up a little.
Yeah.
And now you can't put a room there, so the next one is here. So yeah, you can already see it starting to do things a random number generator probably wouldn't.
And from a player's perspective, I think that's the most pleasant navigation. So I guess, is that something that changes in the filter? Like you add more filtering, you want to control the characteristics.
At this point, I wouldn't change the filter because the filter gets called an incredible number of times. I'd change the fitness function. But yes, you can rewrite the fitness function to control what comes out a lot. Question?
Yes.
Oh,
sorry. I had a question about your starting room. So you showed how the size and the dimensions of the starting room works. Can you do this with 2 rooms? or does this not work?
You could lay down a skeleton of the dungeon with 10 rooms connected by corridors. All it does is it has a list of rooms it's allowed to try, and you can initialize with whatever list of rooms you want. Starting with one room was easy.
Right. Even if they're disconnected, sorry.
Oh yeah, you could start with disconnected rooms. There would be no guarantee it would. Now, it has no clue about connectivity. It doesn't use that. I get connectivity because I'm always putting rooms adjacent to one another, and because of the please stay compact constraint, divide by B, there tends to be far more adjacency of rooms than is caused by the way it's laid down. But no, you could tinker with this system and make it do all.
You build that into the fitness function as well, the connectivity.
Sure.
Yeah, and in fact, what I was saying is building into the fitness function would be a better place than building it into the generative possibility filter, because the generative possibility filter is inside a tight loop.
So there's a game called Rogue, like the shoe, that I think you might be interested in. For two reasons. One is that it actually, like, its dungeon generator kind of has this step in it, not with this sort of complexity and intricacy, but the same kind of requirements of like placing rooms as close to each other, and it's sort of, and so it might be interesting to you to see like how the designer used that and what like weird hacks they put in, and also then there's like later.
I'm willing to steal almost any code.
And then later on, there's like the way that they like render things might be interesting to you as well, because for instance they like merge rooms into lakes and things like that. So I don't know whether that would be like an interesting thing for future explorations of this.
Oh, it would. And in fact, so if I were putting in a lake or something, that would be what I call required content. I want to know there's a lake there. So I'd probably put the lake down first.
So, so I understand what you're saying. But so the way that he does it is, I think there are specific reasons. He's got this really nice talk about why. But like, yeah, by merging rooms, I think you can like retain connectivity elsewhere or something. I can't remember. There was a reason for it, but I'm sure you find it interesting.
Thank you.
Last question.
Can we go back to an image of any of the maps you generated? This. So what would you have to do to get more variation in the size and shapes of the rooms?
Right now, I cough out 4 bits and take it mod 4 to get the room dimensions. I'd have to turn that 4 into a 6 or an 8.
Okay.
No, the things like how big are the rooms are from 2 to 4 by from 2 to 4, and that's for my proof of concept. But you make the rooms as big as you like. And you can also lay down the things you want to be there first and then have the fitness function include, and it has to be navigable. And that's like A star, so it's not real expensive.
Okay, thank you, Dan.